Hello everyone, and welcome to this video I've put together where we will learn how to add resistors in series. In front of you on the screen, you can see I've drawn a really fancy looking circuit with 5 resistors and 1 battery. You can see that the resistors are hooked up in all sorts of weird ways, and our overall goal is we would love to analyze this circuit and figure out the current through and voltage drop across each resistor, basically trying to figure out the overall behavior of the circuit. One of the ways we first learn how to do this type of analysis is through the concept of setting up an equivalent circuit. An equivalent circuit is a circuit with the same battery as the original, but with only one resistor. This resistor represents the equivalent resistance, what we'll call Req, of the original circuit. If a current were drawn from the battery in the original circuit, let's call it current I, then we know that the current is going to go around the circuit, delivering electrical energy to the resistors, and then that current comes back and goes into the other negative terminal of the battery. What I want to do for an equivalent resistance is find one where it will cause the same current to come out of the battery as it did in the original circuit. So as far as the battery is concerned, it gets hooked up to something that is equivalent so that the same amount of current will flow, but instead of 5 resistors, it's 1 resistor. So how do we find this one equivalent resistance? Well, that's where math and physics come in. So we need to know how we're going to combine these resistors together. Notice on my original circuit here that the resistors seem to be connected one after the other. That's called a series connection, or in parallel branches, those are called parallel connections. In this circuit, the current comes out of the battery and goes in through R1. Then that same current leaves R1 and then goes through R2. So it's the overall same current that goes through R1 and then R2, one right after the other. And that is the series connection because it goes through one and then the other. Just like you watch TV series, you watch one episode after another. It's the same current. However, after R2, the current comes to an intersection where there are now 3 possible paths for the current to go. Some of the current will go up and through R3, some of the current will go through R4, and some will go through R5. How much goes through each resistor is a subject that we're going to talk about in another video where we talk about parallel connections. Right now, all you need to know is that there are multiple paths that the current can take. There are multiple parallel routes for the current to travel. So we will say that R3, R4, and R5 are connected in parallel. Now, the rest of this video is going to discuss series connections. There will be another video that will discuss parallel connections. As an example, here are 3 resistors hooked up in series. Imagine they are connected to some battery I'm not showing here, just for simplicity. Let's take these 3 resistors and find an equivalent resistor that could replace the 3 of them. Now, anytime we have resistors in a series, we are going to have the same current through them as there is only one path for the current to travel. This means the current I1 that's going through the first resistor is equal to current I2 and equal to current I3. In other words, it's the same current that goes through each of them. In an equivalent circuit, this same current would have to be going through the equivalent series resistor. So we're going to call that IEQ, but will have the same value as I1 and I2 and I3. We have learned previously that any time a current passes through a resistor, there is also a potential drop, or we call it a voltage drop, across that resistor. There's a voltage drop across R1, a voltage drop across R2, and a voltage drop across R3. So an equivalent resistor that replaces R1, R2, and R3 must have the same total voltage drop across it as it did the combination of that delta V1, delta V2, and delta V3 together. I liken this to a hill analogy, and it's not a perfect analogy, but it works to help you visualize this. A hill analogy where voltage rises and drops can be thought of being like hills. If you were in one of my classes, then I really go into more detail on this analogy. As I just said, it's not perfect, but it provides a useful visualization of what is happening. In a series connection, you can think of each resistor as a drop or a hill that goes down, one right after the other. I've sort of drawn that here. You can see here that my drop is delta V1 for the first hill, that hill being R1. And for the second hill, there's a drop of delta V2, and for the third hill, it's delta V3. And you can visualize the electric current as a bunch of, say, marbles or electric charges moving along the path and going down the hills. With one path, the same amount of marbles and the flow of marbles would have to go through and down each hill, one right after the other. Just as in an electric circuit, it would be the same current that has to go through R1, then R2, and R3. I think you can also see that if we want an equivalent path with only one resistor, in other words, only one hill, then our delta VEQ has to be the sum of all the hills together to create one big hill. So in mathematics, we can write that delta V1 plus delta V2 plus delta V3 equals delta VEQ. The total voltage drop is broken up and shared out to the series resistors. We can now use the current and voltage drop relationships to determine what REQ will actually be. And this is where we can turn to some math. Now, this video is for use in a basic introductory physics course. I don't expect a student at that level to go in and replicate all of what I'm doing here. But as you get going in physics courses and take further courses, you'll want to be able to know how to do this. The first thing we are going to do is apply Ohm's law to each of the series resistors. So right there, I've applied Ohm's law to both the original circuit and the equivalent circuit to get expressions for the potential drops in terms of current and resistance. We know that the voltages have to add together to get delta VEQ. So if we take that previous equation we have here and substitute our Ohm's law expressions into it, we end up with this final equation that relates the currents and resistances. But we also know that I1 is equal to I2 is equal to I3 is equal to IEQ. Since it's all the same, why don't we just call this current I, where I1 equals I2 equals I3 equals IEQ. And you can see that doing some algebra, I can factor out and put in brackets the R1 plus R2 plus R3. I can do the same for the other side, and you can see here that overall, the current I will cancel out. And then what you're left with is you can see that to replace resistors connected in series with a single equivalent resistance, all you need to do is simply add the original resistors together. So in this case, it would be R1 plus R2 plus R3. This, by the way, works for any amount of resistors in series. And you can also probably see that with the more resistors you put in series, the higher REQ will get. Now let's just try a quick actual example to see how this works. Okay, so here I am showing three resistors in a series. There's a 2 ohm resistor, a 3 ohm resistor, and a 5 ohm resistor. If I wanted to replace these three resistors with one equivalent resistor in the circuit, you can see here that REQ would just be adding 2 ohms plus 3 ohms plus 5 ohms. Altogether, that adds up to 10 ohms. So the equivalent resistance of the circuit would be 10 ohms. So adding resistors in series is actually pretty darn easy. But if you have any questions, please get into contact with me. Drop me an email or come visit me in person. I'm happy to go over it with you. Well, thank you for watching, and have a great day.